Great. Okay, so ladies and gentlemen, in this first little exercise, I am going to ask you to work with me to build up a model that's going to be particularly simple. It's going to be almost impoverished in its representation, in that it's going to capture heterogeneity without dynamics. And we're going to go then see how we can add dynamics to such a model at a later point. So I'd like you to now create your first model. We can close this one out. If you want to save the model which you built, you can do File, Save As, and save that changed model, because we did modify it in certain notable ways. Okay? Having done that, I would like you to go to the File menu and close that model. Okay. So you will go here to the File menu. I'm going to have to do Save here. So pardon me, I'm just going to put it into a folder for this boot camp so that you can have access to it later today. Okay, boot camps, and then there we go. Okay, and then we're going to go File, Close. Okay, so you should have a blank slate here on the left-hand side. I would like you to now do File, New, Model. And I would like this to call this simple heterogeneous population. Okay. Now, when you do this, ladies and gentlemen, you should you'll note that you can set the model time units here. It'll say model time units, and I'd like you for the model time units to select days. Okay, it actually won't be a critical issue. Okay, there we go. So I'm going to select days here. There we go. So we're going to say Finish now, and this will now create a new model. And you should see something like this over in the Projects window. Do you see that? You see main here? Okay, so the model is created, in short, with two components. A main class. Do you remember, who could remind me what the function of main was?
That's the environment where the
it captures the environment, the sort of global context for the model. It's the area in which agents live. Now, sometimes we'll have a hierarchical structure, so there'll be main, and then within main there'll be multiple farms, and within the farms there'll be particular, animals and or barns or what have you, and then animals. In which case we might have a hierarchical structure, but main will still be the overall structure for the model. Okay. Now, critically, main is the point of interaction when you run a model with assumptions. Those assumptions will need to live in main, so that the experiment can tell main, assume this, assume that. It tells main what to assume for parameters, which are described in main. Okay. So we're going to come back to main, but first I want to go add a population. Okay. And I'm going to add a population of, and in this case, I have a population of people, and I hope you'll excuse this anthropocentric thing, because I have examples numerically drawn to give incomes, and I'm not sure how we could lend those incomes to deer or moose. Okay, so we're going to say finish ecosystem diversity. And
it's an ecosystem service.
Okay, that sounds good.
No price on everything.
So ladies and gentlemen, I'm sorry, I screwed up. I'm sorry, folks. I should have said add person, not population. New agent type person. We'll say person. You'll notice you could do finish, and that's what we're going to do. You can also specify some features of this person, give them a appearance and so on. But I'm just going to say finish so we see how to do that manually. So it's no magic. Okay, we're not relying on AnyLogic to do it in a way that will leave us stuck if we forget to do it. So I just did new and agent type, and I typed person, and I said finish. That's what I did. Okay, so now we have person. Okay, now, ladies and gentlemen, I would like to go lend this person an appearance. So let's go to the palette. You'll notice when I did person should have come up over here. If you want to see it, or it isn't there, you can double click on person and it should be the one visible. Now, mark my words, it's extremely important that you keep track of which one is the current one being shown. One of the most common mistakes, and it occurs to me as well, but especially to beginners, is that you drag something into the wrong item here. You drag it into main where you think you're dragging it to person. And so it's very important you be clear about, are we looking at person here or looking at main? Because the implications will be rather different if you drag something into it. Okay, so let's go to palette, and let's go down to this pictures area of the palette. And okay, I'm actually going to do something. We could give these. Some of my more mischievous students enjoy making doctors appear as fighter jets, etc. But I will instead suggest that for starters, to simplify things, we're going to go up to presentation, and we're going to make people a simple oval. Okay, less exciting, but a bit easier for our starting point. Probably starting tomorrow, we'll start using person icons, which adds some extra texture to them. Okay, so we're going to use a circle, and you can shape it visually. Another way you could do it is in the properties of circle. By selecting circle, we're doing properties, you can set its radius. And I'm going to set its radius to be 10. Down here in properties. And I'm going to set its x location to be 0 and its y location to be 0. Okay? Those are fixed numbers we're typing in there. So we just directly type them in to this. How did I do that? I selected it. I then scroll down to the position and size area, and for x I put 0, and for y I put 0, and for the radius, ladies and gentlemen, I put 10. Is that okay? Are we okay with that? Okay, good. Okay, so who would like a bit more time? Keenly aware that a TA is not on the prowl, and it makes me want to go a little bit extra cautiously. Okay, so ladies and gentlemen, we have lent people there. We've given a theory of personhood that right now is singly impoverished. It includes representing people as a circle. But let's give them a location as well. Okay. Well, first let's put them in a population, and then we'll give them a location. Okay. So here they are. We have a circle here. Let's create a population of people. Now, mind you, it is easier to do this after you define a presentation for a person. There is a way to do it. Yes, it's easy. If you do it before you define the person's presentation properties, their appearance, you can do it, but it involves a little bit more work. It involves pressing an extra button. So let's go to main. The population for the person is going to live in main. So how do we create a population of people? We go to main, and we drag in person. And we call it population. Okay? And this is going to be a population of agents. Not just a single agent, but a population. So how did I do that? I just dragged in person to main, and I let it go. So I clicked on it here, dragged it over here, let it go, and then I changed its name to population. You can change its name. I'll do it again for those who want to catch this. Drag it in, and I can either change its name here, or I could go down to the properties menu and change its name here. Are people okay with that? Okay. Ladies and gentlemen, The next thing I'd like you to do is, when you have this population selected, indicate that it's a population of agents. Not just a single agent, but a population of agents. And we will initially let the initial number of agents be 100, okay? Is that okay? We okay with that? Okay, ladies and gentlemen. Does everyone have a population now? Okay. I would like you now to run this model. You have created your first runnable AnyLogic model of significance. So how do we run this model? You tell me. Right click on this, right click on the scenario we want to run, the experiment, and we want to run it. Okay, so here is the results of running the model. It is unimpressive, but you have to start somewhere. There is a population of size 100. You can see it here. If we click on this, there's 100 people there. You can also pull this down. There's 100 people in the population. But where are those people? They are all stacked up atop each other in a most unseemly fashion here. Okay? So let's give them each a location, shall we not? Okay. So go to population. And you'll notice in the population there's a thing that says initial location. Okay? This is one of two ways we can give them a location. This is the more robust way. Actually, it's one of a bunch of ways, but this is one of two very common ways to do it automatically. Okay, in population, initial location, I'd like you to set in the specified point. Okay? For the X location, we're going to enter something. And this is going to be your first use of the generality of AnyLogic's AnyLogic's mechanism of being described. So you're going to type uniform 0 through 100. What this means is when it comes time for a given person to determine their X value, it will run this formula. And this formula is actually what's called a Java expression. It actually will run this, it will call off to a uniform function, so-called method, with values telling use a minimum of 0, maximum of 100. Okay, now, how do we know about that? Well, if you go and you start typing uniform, you don't have to do this, but I'll start doing it. Uniform, and you press a certain button on your computer, control space on PCs, you will see a set of possibilities that you can type in. Okay, and for some of these, the ones that have ... as all of them do here, you can actually see there's several possible ones. So, for example, uniform, and I'm going to choose this one here, uniform min max. Okay, minimum and maximum value. So this control space, I think on Macs it's command space or alt space that will do it. Control space on PCs, I think it's command space. You can get it to tell you what's possible here, and you can select. You notice it gives you information on each of these. Gives you information about what they assume as their arguments, what information they need to do their job, and then what they give you back. In this case, it's drawing a value uniformly, a continuous uniform value between 0 and 100. Okay? Are we okay with that? Okay, ladies and gentlemen, for each agent in the population, it will be determining their X value by drawing from this, their Y value by drawing from that. Let's now run this model. What should we see now, do you think? Okay, we see that. They're drawn from 0 to 100. Let's make it a little bit more expansive. How do you think we'd make it draw it from 0 to 500? Can anyone tell me what to do? What would I do here?
Just go into population, go to initial location,
Yeah.
uniform 0 to 500.
To 500, yeah. So let's do that. 0 to 500. Okay. Great. Ladies and gentlemen, there we go. You see that? Something like that? Okay. So these are the individuals in our population. Each of the 100 people in our population is depicted there. We okay? Okay, ladies and gentlemen. Now suppose we wanted to run a bigger population. Where could we go to run a bigger population? Where is the population size set? Anyone remember?
Just above them.
Okay, so yeah, it's in population. In general, in a model, particularly for veterinary science models, you often have metapopulation models, models with more than one population included in it. And remember, a population's characteristics, the particular assumptions about those characteristics, the parameter values used for them, that's specified in the associated with the population. Personhood or deerhood, swinehood, that's defined in the person class or the swine class. But the particular assumptions about the people in that population, those are defined in the population. So in the population, we specify the number of agents. So we could change it from 100 to 1,000, for example. Let's run it now. 1,000 agents. So how did I do that? I went to main. I went down main, and I went to population, and I went to set the initial number of agents to 1,000. Do you see that? If you go down main and you go to population, initial number of agents, 1,000. Okay? Now let's run the model. What should we see now? Okay, it's denser. But frankly, that's inconvenient and awkward if every time to change the population we want to run a scenario where we have different population, we have to go in and change it right here. We have to go change the model structure just to run another scenario and then remember to change it back after we run that scenario. That's awkward. It's tedious and it's error prone. We might forget to change it back. We get that call in the middle of it and we go out to lunch with someone, we come back, we've forgotten that we changed it, we send off that paper for review, and then we realize, oh, I forgot to change that value back before I sent it off. Okay, so in general, ladies and gentlemen, we don't like to have to hard code values into the model. It's error prone. It's obscure. You don't know what the value is. So ladies and gentlemen, we're going to add something that's going to be a dominant theme between now and lunch, besides your hungry stomach. Ladies and gentlemen, we're going to add in a way of characterizing an assumption about this model. An assumption and communicating it to the model in this case. We're going to communicate the assumption about the number of people in the population, the population size. And the construct to do this in AnyLogic, which is going to be a key construct, one of the most important is a parameter. Okay? So let's go add a parameter. Okay, so ladies and gentlemen, go to palette. Remember, palette provides the palette from which you will paint the canvas. And you're going to go to the agent item in the palette. And you'll notice there's a parameter there. And you're going to drag that in. And you can use the aesthetics, your own aesthetics, to determine where it will go. I'm going to put it next to population. And I'm going to call it population size. Generally speaking, in AnyLogic, it doesn't let you have spaces between things. This is conceptually two words, population, space, size, but it's not going to allow that. Java is a singularly unforgiving taskmaster when it comes to names. It is case sensitive, meaning it cares about whether it's upper or lower case, and it will not suffer spaces in its names. Okay? Which is most unfortunate. There's two ways to get around that. One way is you can use an underbar like that. Some people like that. The other way is you use what's called camel case. You capitalize each new word. And I tend to be partial to that. So I'm going to call it population size like that. Okay? Population capital size. Now, this is a count. It's a count of individuals. It's not a double precision value. We don't have 32.3 people in our population. I want to highlight that, actually. We recently had a paper published in, I think it was JID, Journal of Infectious Diseases, where we found marked differences between the results of a compartmental model if you assumed fractional people or not. It was particularly, I might note, for the case of AMR, so antimicrobial resistance to gonorrhea. And it made a profound difference at a policy level in terms of what was recommended and what would obtain. And the only way we found that is we took this compartmental model, and we were interested in investigating things in more detail, but we built an agent-based model out of it. And agent-based models, by their nature, depict individuals, agents. And we discovered marked differences in the results. And we thought, wow, that's really interesting. I wonder if it's coming from the assumptions of a fixed network. We relaxed that. We assumed random mixing still was a difference between the two models. Could it be because heterogeneity we can capture in an agent-based model that it's hard to capture in the compartmental model? Wasn't that? We kept on relaxing assumptions until the two were virtually interchangeable, with the exception of the fact that people were individuals and quantized as individuals. You couldn't have a fractional person. Big difference between the two models. Then we created a compartmental model where they were limited to having no fewer than one person infected. Made a night and day difference from the original policy results. Be advised, quantization can matter. In an agent-based model, it's generally an asset that you can only have a count of individuals. Because this is a count, though, it's not a double precision value. It's not like 3.14159. It's an integer. An integer, count 0, 1, 2, 3. In this case, it's a positive integer. Okay? Population size will be an integer. We could specify a default value. If no value is specified, what value to use? And I'm going to say 100. Okay? Okay, this is population size. Ladies and gentlemen, now we need to operationalize that. We want this to be our population size. Where is the population size in this model depicted right now? Can anyone remind me? Wherein does it live?
Maine.
It's in Maine, indeed. And where in Maine? In Bangor? Or in Brunswick? Okay, it's in population. It's in population in Maine. Okay? Population size is what we want for the initial number of agents. We want it to use, whatever it's going to use, for the initial number of agents, it should be whatever specified by population size. So we're going to say initial number of agents is population size. Now I want to highlight a fact that may have gone unnoticed. It's a fact that's minor in its visual detail, but major in its significance. When you have fields in AnyLogic to be filled in, an example would be number of agents, X and Y, often by default they show numeric number, 0, 10, whatever. But in general, you can fill in a formula there, a formula like this. You can fill in a reference to a variable, for example, population size. So don't be fooled into thinking just because there's a number there initially, you're straitjacketed to numbers. Far from it. Generally, you can fill in lots of things, although occasionally there may be an indication you have to say this is a dynamic quantity. We'll come to that. So this should be population size. Now, why have we done that? If we just want a population of 100, well, because this lends us flexibility. May I show you why? Watch this. So, having done that, having the population now be specified population size, and this is the population size, now each simulation, each experiment can specify a different population size. This one will be population size 100. I'll say, pop size 100. I'll just name it pop size 100. I'll create a new experiment, and this will be called, pop size 1,000. And I can now run a population of size 1,000 with this experiment. This is really useful because I don't have to go in and tweak the model every time I need to rerun an experiment. I just rerun a defined experiment from before. This captures all my assumptions that the model needs to run it. I don't have to muck around with the model details and forget to change them back and forget what their the original values were. It's all encoded in the experiment, okay? So parameters, mark my words, because we're about to build on this in a major way, in a profound way, in the next 15 minutes. Parameters, ladies and gentlemen, encode assumptions. Parameters communicate those assumptions from a point where this object is being created, which in this case is in the experiment, to the object itself. So if the parameter is in main, the parameter value is specified by the experiment, and it's told to main, use this. And main says, that's my assumption for now. If the population size is 100 or it's 1,000, whatever the experiment you want. So parameters encode an assumption and communicate that assumption to the thing which includes that parameter. So parameters in main. So experiment specifies that the value of that parameter to main. And that allows us great flexibility in running different experiments, rerunning them. Whenever we update the model, we can just rerun these set of experiments we've defined before with certain assumptions without mucking with all those assumptions in the model. Okay? So here's the population size. And here we'll run these two, and I'll run it, and we will see it in all its glory. There it is. And let's again, and here's with the big population. And for those who are seeking for a special thrill, you can do a new experiment, and you can have a pop size of 10,000, and we will encode that here, and you will see a suitably dense population result. Okay? Boom. Okay, so ladies and gentlemen, parameters encode assumptions. So we're going to now take that to the next level. We're going to now create a heterogeneous population. Right now it's heterogeneous in location only, and that's the starting point. But now we're going to add characteristics to people. Okay? So, ladies and gentlemen, I would like you to first add a parameter here, which is going to be it's going to be the age parameter. Okay? So let's go to person. And we're imagining that we're simulating an outbreak, say, where age can be reasonably viewed as more or less fixed for a person for the sake of that outbreak. Maybe it's a flu outbreak. And even though people in reality age, we're not dealing with major demographic change over the course of this flu outbreak. So we'll model a person's age as a parameter rather than as a change in quantity. Soon enough, probably starting tomorrow, we'll start to treat age as something which will change over time, and you can have a continuous age. But for the moment, we're going to treat it here as a fixed quantity, a parameter. Are you ready? Okay. Now, we want to associate each person with some assumptions about that person's age, and we want to communicate that assumption to them from the population. What would I use to encode an assumption and communicate that assumption? A parameter. Good. So we're going to add a parameter to person called age. Okay? So how did I do that? I went to palette, went down to the agent area palette, and I dragged in parameter. And this is called age. Okay? And it is a double. It's a continuous quantity. Parameters can encode continuous quantities. Note this is a bit different from compartmental modeling, where if we wanted an age-stratified population, what we would do is divide it up into age categories. Unless we wanted to build a PDE model, a partial differential equation model, which is a whole another kettle of fish. It's a lot more sophisticated. But generally for an ODE model, for a compartmental model, we divide it up to age categories. And I've done tons of those models and have tons of examples if people wanted to see them, including one I provided to you as part of the models. But one of the advantages of an individual model is we can use age that's continuous. We can use characteristics of a person, be it age, be it income, be it birth weight, that are continuous. Now this has some advantages. If you want to, for example, divide up a population into age categories that sometimes need to be summarized one way, sometimes another, or if you want irregular age categories, often keeping it as a continuous quantity is more favorable. So we're going to describe this as a continuous quantity. Okay? Okay, so ladies and gentlemen, we're going to have age as a quantity, and we are going to, so we've specified this as an assumption associated with person, and I mentioned earlier, who's going to specify the age? The age characteristics of the population, who's going to specify that? The begins with P, ends with N. Okay, the population is going to specify that. So let's go over to population in Maine. So I went to person, I added age as a characteristic. They have a characteristic of age. Let's go to the population in Maine. And ladies and gentlemen, you will notice now that in this population for Maine, there's a formula expected for age. Okay? We want to draw this from some distribution. Okay? Now, there's a branch point now. Would you like me to, so one way I could do this is to draw it uniformly from a distribution, or draw it from a normal distribution. Another, truncated normal, another way I could do it would be to have a custom distribution. We could actually see, if I had a population age pyramid, for example, how I draw from it. Which would you like to see? Would you like me to do that later, or do it now?
Maybe now.
No? Okay, great. It's easy enough to do. If you'll grant me the liberty of quickly specifying the custom distribution, bearing in mind that you can put it in any one you want. So, into Maine, go to the agent palette and drag in a custom distribution. Okay? Custom distribution object. And this will be called age distribution. Okay? Okay. So, ladies and gentlemen, I would like to define it now. We're going to define this age distribution for certain ages. So between 0 and age 10, maybe we have, this is just number of observations. It's really giving a probability density function. It's defined over continuous age. So these are just relative values. 0 to 10, 1,000 maybe, 20 or 10 here to 20. Maybe I have 1,200 or something like that. 20 to 30, I'll have 1,100, and 30 to 40, I'll have let's say 900, and 40 to 50, I'll have 950, I don't know, and 50 to 75, I'll have 2,000. We could choose whatever age category. 75 to 100, I'll have 500. Fine. Okay, so you'll notice, by the way, it draws it below. It draws samples from it below here. And this is an age distribution that I can define in a couple ways. I can define it with a frequency table, or with observed samples that I could draw from, or with ranges. So, ladies and gentlemen, having done that, now let's go back to the population. The exact numbers here are immaterial. Does anyone need me to just pause more here, or to ask a question? Custom distribution?
I didn't get the preview.
Oh, okay, so what's below it?
Nothing.
Does it need to be expanded? Is it possible? It's like,
It's possible.
you have to expand that?
Yes.
Yeah, there's actually quite a few, thank you for highlighting this. There's quite a few things in AnyLogic that use these kind of expander things, and so if it's pointing sideways, it's probably an indication that if you click on it, it will expand. downwards. Okay? Okay, ladies and gentlemen. So let's go back to population. Now let's draw from that distribution we've just defined. So age will be defined as a draw from age distribution. Now you'll notice that there's this begin paren, end paren. That means actually call it. Treat it like a function. So actually say, give me a draw from the age distribution. It calls off, give me an age, and it will give you back an age. So this is requesting that it do its job. By contrast, if you gave this, it would say, you're giving me a whole distribution for age. What do I do with it? This is telling it to draw from it. Okay? Okay. Okay, so that's good. So, ladies and gentlemen, let us now run this model. Shall we not? Okay, so let's draw it from, I'll draw it from the pop size 100, doesn't matter which one. Okay, here we go. And now let's go down and drill down to the level of an individual. Here's someone of age 60.25, 9.6, 43.4, 64.49. Sorry. Okay, so we have people of different ages. Do you see that? Mm-hmm. Okay. Okay, so, ladies and gentlemen, we have now a heterogeneous population. Heterogeneous not only in terms of location, but in terms of age as well. I'd like now to add in two other characteristics, if I may. Okay? The first is, I would like to add in to a person the fact that they have a certain sex. Okay? How would I do that? You should tell me. Where do I go to add in a characteristic to person?
To person.
To go to person, you bet. Persons encode their own characteristics. Now this is actually a non-trivial point because there's a certain amount of modeling done at an individual level that's done in tools like MATLAB or Mathematica or R, where basically what you have is you don't have people captured as people, but rather you have a vector of, say, ages for each successive person in the population, and then a vector of, incomes for that person, a vector of latitudes, a vector of longitudes. And so there, each individual's characteristics are actually stored in different vectors at the same index in different vectors. Here, the characteristics of a person, the behavior of that person, their state, the assumptions we make about them, their behavior over time, that's all stored in person. And this is what we call an agent-oriented or object-oriented view of things. We wrap up their data, their behavior, all in one place. It's associated with person. And it turns out that makes certain things much easier to represent. And things like network structures, for example, are very amenable to it in a way that they're not quite so nice when you represent things across large vectors. Okay, so here's person. We want to add in a sex for them. So what do we need to do? What do we need to add to person? Anyone? Yeah, we want to add a parameter. And this parameter is going to be called sex. Okay? Now, ladies and gentlemen, the next choice will be, what is its type? And here, the plot thickens.
Always does.
Okay. Okay, so we could use a Boolean with women denoted as true, as the truer sex. Or we could use an int where men are 0 and women are 1, for example, or 1 and 2. But the problem with those representations, so they'd be perfectly functional, perfectly good, and in fact we've had models which have used those conventions. Biostatistically, we often use 1 and 0 or 0 and 1 for different sexes. The problem is it's not very transparent. When you see a 1 as someone's sex, you have to remember back, is that a male or female? I can't remember. And it turns out there's a better way to do it. And AnyLogic supports it after our injunction thereupon. So, ladies and gentlemen, I'm going to show you a new characteristic, okay? So, we're going to have sex, but we're going to hold off for a moment telling what type of thing it holds. Boolean, integer, double, until we do this next thing. So ladies and gentlemen, I would like to add to this population, to this whole model, a thing called an option list. And this is going to be sex with a capital SEX. And what that capital means is it's going to define the set of possible sexes someone could take on. And so there's going to be female and there's going to be male as two sexes. And this will give them nice names. It'll make it very clear if we have a sex what it is, if male or female. Make it crystal clear. So when we're browsing those people or when we output them to an Excel sheet or to a database, we can actually use male, female. Okay? So, how did I do this? Let me rehearse that again. I went here, I right-clicked on the project as a whole, I did new, and I chose option list. And I made a capital SEX. Capitals indicate a set of all possible things, like capital P person here, set of all possible people, as it were. It's personhood. Capital SEX is going to be the set of all sexes, okay? And there's going to be female, and there's going to be male, okay? Okay, and I'm going to say finish. There, it's been added to the model. Okay, now we have a way of encoding sex. It's a set of possibilities. We don't need to use no ones and zeros or double precision values. We don't need no ugliness in our model. We instead will go to sex in person and we'll choose other, and we will say capital SEX. Okay. Actually, now that I think about it, it's already there. So we don't even have to choose other. I'm sorry. We could do it that way, but it's actually listed now, sex. So we give them a sex. This, for a particular person, this will be a specific sex. They will be either female or they will be male. And the type of it, however, is capital SEX. Okay? Okay. There we go. So, ladies and gentlemen, this will be the type of that. Just in age will be a double precision value, 32.3 years old. Sex will be male or female. Does that make sense? Okay. So, ladies and gentlemen, let us run this model now. Oh, sorry. No, there's one thing we have to do. One thing we haven't done. What haven't we done yet?
Decide how many are male and
how many are male and how many are female. Okay. So, we can go back to the population, and we can do this in one of we could do it one of three ways. And each of them enjoy virtues to recommend them. We could do a sex distribution, a distribution over sexes. That's one possibility. We could specify precisely. We could pick with 50% probability one or the other with a very simple expression, or we could roll a weighted dice, flip a weighted coin as to which is desirable. So which would you like to do? Does anyone have any preference? Okay. Okay. So sure. We'll do a sex distribution. Let's do that just so you can see how it's done. Custom distribution. Here we go. Custom distribution, this will be sex distribution. Boom. There we go. The type of this, which do you think it will be? Remember we had an option list for sex. What type will it be? Continuous, discrete, or options? Options indeed. And the option list, we have to specify is sex. Okay, good. Okay, male and female. Number of observations for female will be 51 and male will be 49, let's say. They could be. Okay, so 51% of the population of the births will be female and 49% male. Okay, ladies and gentlemen, now let's go back to population. Well, here I should give you some time. Are people still working on that sex distribution? Okay, 51 male, 49 female. How did I do that? I chose the type to be options and the option list to be sex, and then for each of these options, I specified the number obtained. Are you ready for that? Okay, ladies and gentlemen, is everyone ready to move forward? Okay, go to the population, And now, where do we specify in the population? Where do we specify the characteristics of the population? It's up at the top for sex. So what would I need to do to draw from that distribution? Anyone?
Sex distribution.
Sex distribution. Yeah, exactly. Sex distribution. Boom. By the way, notice AnyLogic is incorrect there. It says it returns a double. That's not correct. It returns an option list. Okay. Okay, great. So let's run the model. Let's run the model. Okay, excellent. So here we go. We're going to run it. Boom. And now let's go drill down to a particular person. Here's a female who's 60.25 years old. Here's a male. Here's a female, 35. A male, 41. Female, 53.5. Female, 54.61. Okay, so now we have heterogeneous population. Okay, ladies and gentlemen, we're going to do something a bit different now.
Can I ask a quick question?
Please.
What if you want the sex distribution to be different by
Yes.
age class?
We're about to do that.
Oh, okay.
We're about to put in those things.
Okay, good.
We'll see how that's done in just a minute. But first, I want to add some visual pizzazz to what we're looking at. We're going to make the visual appearance of each of those circles be different for men and women. Okay? So I'd like you to go to person. And in person, I'd like you to select oval. So we're going to, as a general rule in AnyLogic, if we want to have something have a certain characteristic, we go to that thing, we select it, we go to its properties, and we give it that characteristic. So here, for person, we select the oval, and we're going to set the fill color of this oval to be different for males and females. Now, watch this. This is an important point. So just to be clear, we're in person here. We've gone down to person. We select the oval, and we scroll down the oval to appearance. For the fill color, ladies and gentlemen, you'll notice right now we can pick a fill color. But that will apply to everyone. It just says, what's the fill color of these ovals? And, I could pick a color, but it'll be used for everyone. We want it to be different for males and females. So how are we going to do this? Well, you'll notice next to this thing that says equals, but there's a thing, if you click on this, there's a thing called dynamic value. We want it to be dynamic value. We want it to actually be set while the model's running, not something that's predefined. Okay, ladies and gentlemen, we're going to say if they are female, there'll be one color, another. Okay? So if the sex equals female, if their sex is female, if it's that, we're going to use one color, otherwise another. So question mark, and a sort of neutral set of colors that's been suggested for my boot camps is yellow and gray. That we've had some disagreements in the boot camps about what colors to use, and I don't want to go there. So so yellow and gray. Okay, humor me that. So females will be yellow, men will be gray. Okay. This is how you write if then else expression, a formula. So if this is true, use this value, otherwise use that value. And that's what's being asked for you. It's a value, a color. So yellow, otherwise gray. So if they're female, you notice double equals. That's testing, is it equal? If you did this, it would be actually trying to make sex be female. And this is it female? If so, use yellow, otherwise use gray. And that's just how we write it. And I know it's the most unpleasant thing to look at. But I've looked at worse things, and if you're a vet, so have you. Okay, so shall we run this? Mm-hmm. Okay, so let's run it. Okay, there we are. So who are the grays?
Male.
The males indeed. And the females are the yellows here. Okay? Okay, now, to address the question, remind me your name?
Amy.
Amy. So to address Amy's question, what if we had characteristics which are not independent? I mean, it's all fine and good that here in Maine we have this population where we have each each characteristic drawn from separate distributions. But in general, we're going to have some covariance between these things. If we're dealing with real data sets, we're going to have some statistical patterns that will mean age is not independent of sex, or income from age, or what have you. And I'm going to show you how we can take these into account. Okay? There's actually several ways. And one popular way within tools like AnyLogic and agent-based models in general would be to actually sample from the population. You could have each person in the model be drawn from a certain person in a database, correspond to a certain person in a database with certain characteristics. And that is readily done. We won't talk about that till later in the boot camp if you're interested, but it's actually quite readily done in AnyLogic. And basically it involves assigning each person an index, and then them, right where this is done here, you would read in from a database those characteristics for person number I. So person 100, and the next person 101, it would read in what is my age, what is my sex, and you can impose that. So it's a very general mechanism, but here suppose we wanted to use different distributions. Okay, so I'm going to add one final characteristic to person here, if you humor me, the anthropocentric viewpoint. I'm going to add in from palette an income parameter. Okay, income. Here we go. And that too is going to be a double. In other words, it would be some floating point quantity. Could be, they earn $1,000 per month, what have you. Okay, ladies and gentlemen. Okay, now, so we have income for each person. Where do we specify the income associated with the population? The income distribution from which to draw the income of each individual. Where is that specified? From whence does that come? It's in Maine. And where in Maine? Yeah, population. There we go. Good. So the population, remember personhood, the fact that a person has an income is defined in person, but the characteristics, the particular assumptions about that income will differ from population to population. So that's specified by the population. We don't impose a distribution in person, typically. That's an aspect of what environment they're in and so on, and it's associated with the population. So different farms with different populations associated with age distributions associated with animals or what have you. Okay, so the income here. We are going to first, we might as well cut to the chase. We're going to, in observance of the fact that there are very unfortunate sex-based disparities in incomes, which obtain, even for the same sort of work, we're going to reflect that in our models showing different sex-based income distributions, okay? So here, we're going to put in an expression that if this person is male or is female, we'll use different distributions, okay? So if they're female, we'll use one distribution, male, we'll use another, okay? So given what you've learned, how would I do that in AnyLogic? We just saw a similar expression to show their color. How would we do it here? How would we test? Are they female?
Equal.
Yep.
Female.
Good. Okay. And then what was that funny character that was next? Question mark. Okay. We're going to use one distribution. And here we'll draw from a log normal distribution. Log normal with log mean 10, log standard deviation 3, and minimum value, which is not going to be binding here, of 0. In other words, this is mu, this is sigma for the log normal distribution. Otherwise, what was that other funny character that goes here? Colon. Otherwise, we're going to use 11 and 4 for men. Okay. These are, of course, floating point values, so we can make 10.35 or whatever. So we're drawing from two log normals. This log normal distribution will be for men, and this one will be used for women. Okay? That's how we're doing that. That's for sex. So now we're having two different distributions. Now this isn't the only way. As I said, You could draw values from a database. You could also draw them from, different custom distributions for each value, for each age category. AnyLogic currently does not have a nice built-in mechanism for multi-dimensional continuous sampling, but you could readily use a library, a Java, for example, the Apache math library, which supports, if I'm not mistaken, multivariate log normal and normal distributions, and you could draw from those. Because this is Java after all, and that's in Java. And we do that in our AnyLogic models. We'll draw from those distributions in other libraries sometimes. Okay, so here we go. So let's run our model, and then we'll add a tiny bit of pizzazz. Oh, it's unhappy. Okay, look at that. Sex cannot be resolved to a variable. Okay, yes. Okay, well, this is one way to learn if it's unhappy. So what happened there? How did I know it was unhappy? Well, I went to run it, and it complained. Watch this, run. And it will say, proceed with launch, error. And you'll notice there's a thing down here saying one error. Do you have that? Okay, another way to know is to use this button up here, build model. This will actually test, does AnyLogic understand your model? I do this all the time. Does it understand what I mean? Does it understand what I told it to do? And if it says no, it will say error. You can click on these errors. It will take you to problems window. Double click on this and it will say, I don't know what this X is. So the trick here, ladies and gentlemen, is we actually have to say self.sex, my sex. Okay, it's referring to the fact that I'm dealing with my sex here, my age. This is an unfortunate thing. It occurs in 2 or 3 places in AnyLogic. That we have to refer to this self thing, and there's a trick to find out when it is, when you have to use it, but this is the main place I encounter it. Okay, so having done that, we could build here, and it's a happy camper. If you click up here, build model, it'll say build completed successfully, or you could just run the model, and it will be happy. Let's go down and look at the population. Here's a population, here's a person with an income of $18,000. It is a woman. Here's a woman with a lower population, a woman with a modest population, and here is a very well-heeled woman with a population of over $1 million. So, ladies and gentlemen, let us, with an eye towards visual clarity of the model, visualizing things. This was one of the areas which people expressed in feedback some interest in. Let's go to person, and we want to make the oval size depend on their income. Ladies and gentlemen, can you describe to me where I would go within person to make the oval size depend on income? Anyone?
Oval.
Yeah, we go to oval. And in the oval, we have to look for the characteristics of size. And there's a radius. Now, I told you before, in general, where it has a number, you can put other things. But this is a key point. We can't actually put this right here. If we start to put an expression here, it'll say invalid number. The key thing here, ladies and gentlemen, is see this equal sign before? We saw this before. We have to choose dynamic value. And then we can actually set it to be a formula. So we will do log here of their income, okay? Log of, and we're going to make it income plus 1 because we don't want to deal with an income that's 0, times 2, okay? Times 2.0. I've just chosen a nice formula that will lead to things that aren't too massive or too small. Okay, so let's go. So I'll put that up there again. And actually, I would do plus 1.0 just to be consistent. There are places where it's not one of them here, where if you use integers, things are done a little bit differently. This is a case where, oh my gosh, what mode am I in here? Okay, this is very, very, okay, so I'm in numlock mode. Is that what's going on? Okay, times 2, 2.0. Okay, fine. Okay, are you ready for this?
Wait, are these just arbitrary units on a radius?
For radius, it's in arbitrary units.
Okay.
Yes, yes. It's just to make it to prettify it a bit. So there we have it. So now we have, who are the big individuals? Unfortunately, and men who are what? Who are high income men, right? Because remember, we set the radius to be dependent on the income. Smaller individuals are people with lower incomes. So, for example, here's someone with this modest income, a small income, medium, large, etc. Here's a man with a Trump, is this? No. So he's a very large monthly income. He's also in debt. Well, okay, never mind. But yeah, he's this size shows the income. So we've shown how to make their visual appearance depend on their characteristics. Okay, so let's take stock of what we've seen here, and talk a little bit about its implications. We've done something which is at the level of, in terms of the functionality listed, it's very modest. This is a dynamic model in name, but it's actually not exhibiting dynamics. We have static characteristics as of yet. But we've done something that, on the other hand, is pretty significant if you looked at in the landscape of dynamic models, because we do here have continuous characteristics associated with individuals. Those characteristics can be readily drawn from custom distributions or conditional distributions, and they can be readily hitched up to, wired as it were, in a declarative fashion, a fashion that doesn't really require much in the way of any sort of coding. They can be wired up and told to depend on those characteristics. Hence radius, we gave a little formula for it, and fill color, we gave a formula for it, and we basically said go figure, and it went and automatically draws these things according to those rules, as it were, that we specified. The fact that we can have a heterogeneous population with continuous characteristics is significant, and there are times where having those continuous characteristics are really important for summarizing data in a flexible fashion, a fashion that might be different for one model user versus another. Maybe one wants to break up the first year of life into several sub-age categories, while another wants to see at a coarser level. And we don't have to broker that distinctions with the model structure like we would in an aggregate stratified model, where we have to pre-decide on age categories. We, moreover, have the luxury of having characteristics of an individual that are continuous in ways that might affect their later life course. For example, birth weight, we could use very fine, we have this great precision we can use, which might shape their later risk of chronic diseases in a way that would be hard to capture in a stratified model at an aggregate level. So we do have a heterogeneous population, and indeed, the capacity to capture heterogeneity is one of the persistent draws of agent-based models, because stratified aggregate models tend to blow up as the number of distinctions, the number of classes of heterogeneity rise. And typically you can only keep track of discrete categories, often rather coarse ones at that. So we have this model. We've shown how it can include visualization properties that reflect the heterogeneity in a way that can sometimes lend insight. This is not merely eye candy. Here it's a little toy example, but in general, visualizations play to some of the strongest features of a modeler, their ability to recognize patterns visually. It's one of the strengths of us as a species, and by using the right visualizations, often you can come to insights that will be hard to get from columns of numbers coming out of a model. So, some simple features of this model shown to us. But ladies and gentlemen, This model as yet lacks, despite the advancing date here, despite the fact we could speed up this model and have it proceed through time, there's nothing changing. There's nothing being modified over time. And it is to that task that we will turn next. And we will bend AnyLogic to our needs in terms of representing processes that will govern an individual by showing progression among states. Now, Sean, I need to ask, when is the designated time for lunch? Because I want to pick my battles carefully here.
We could probably break now and then relocate over to Pomeroy.
Yeah, so this room has our every other week research seminar in right now, which is actually interesting as someone who thought would be in this room, right? So Katie's doing her coyote model.
Oh, neat. Neat.
For this. So it would also be somewhat interesting to this conversation, the seminar coming up. But that is in 5 minutes.
Oh, I see. Okay. So we'll probably vacate for that. I mean, you know, if there were a desire to watch it, that's certainly good with me. If you were thinking that it might be combined, but otherwise, I guess we'll be going over to another room. Is that right? In this other.
Yeah, and then I'll take you up to Subway so you can get something to eat.
Oh, fantastic. Okay.
So the title is Infectious Diseases in Urban Coyotes, What Factors Influence Exposure Risk? Not using any logic basis.
No.
Oh, yeah.
I have screwdrivers and things other than hammers too.
Yeah, so one of the classes I teach, one of the reminders